Swayam Prabha. Digital India. Educated India.
Right. So we are now in our 10th lecture, and here we are going to discuss the linear programming special cases, and this is going to be our third lecture. And specifically, we shall be discussing linear programming problem in non-standard form. Now, in this, non-standard form, first of all, we shall discuss the various standard forms of maximization and minimization, and thereafter we shall see that how different non-standard forms can arise. And after that, once we understand that what are the different non-standard forms, thereafter we shall try to see how to solve them by using the simplex algorithm. A few examples we shall be taking up, and based on those examples we shall try to understand those non-standard forms. Right. First of all, this is the maximization problem, linear programming problem in standard form. This already we have discussed in detail, and here is it once again. Maximize z equal to sum over j equal to 1 to n cj xj, subject to j equal to 1 to n aij xj less than equal to bi for all I equal to 1 to m, and xj greater than equal to 0 for all j equal to 1 to n. So this is our maximization problem in standard form. Now here a number of matrices are there. First of all, we have xj. Xj is the number of unknowns, and they are n in number. All right. Cj is the profit coefficient associated with individual xj's or individual decision variables. So if you expand, it will be like C1 x1 plus C2 x2 plus C3 x3, etc. And when it comes to the constraints, we have the coefficient matrix, that is Aij, which is a single term of the coefficient matrix, and Bi are the availability of the different resources. So Aij xj is the total resource requirement of a particular type. So we are assuming there are m different resources. So it is like A11 x1 plus A12 x2 plus A13 x3, etc. Less than equal to B1. So that is the equation for the first resource. Similarly, for the second resource, third resource, and there are m number of resources. So all m resources, this particular constraint will be repeated. So one thing you must also note that for a maximization problem in standard form, the standard constraint type is less than equal to, right? So all the constraints are going to be less than equal to in the standard form. Then we have the variable type. So that is the non-negativity constraints, that is xj greater than equal to 0 for all j equal to 1 to n. What does it mean is that all the variables are greater than equal to 0. That means the problem is to be solved in the first quadrant only. Is it all right? So that is maximization problem in a nutshell. There is a linear objective function. There are a set of linear constraints, and in a standard form, all the constraints are less than equal to type. And we also have non-negativity constraints where all the variables are greater than equal to 0. So that is maximization problem in standard form. Now, minimization problem, on the other hand, in standard form, again, the objective function is one of minimization, z equal to sum over j equal to 1 to n, cj xj, subject to, sum over j equal to 1 to n, aij xj greater than equal to bi. So in minimization standard form, all the constraints are greater than equal to type. So usually in minimization, what happens that, we have to, let us say if Cj is a cost parameter, so total cost we are trying to minimize, whereas different operations must maintain a certain level, right? That certain level is represented by the B matrix. So B1, B2, B3 up to M. So that means the total activity that is going on with the different decision variables, which is represented by sum over Aij xj, that should be greater than the threshold value. Is it all right? That means that much of the activity has to be maintained. And also the non-negativity criteria, so that the problem is solved in the first quadrant only, are also to be maintained, which is xj should be greater than equal to 0. So in a nutshell, we have an objective function which is minimization. We have the constant type, all are greater than equal to, and the non-negativity criteria should also be satisfied, that is greater than equal to 0. That is the minimization in standard form. So we have seen the maximization linear programming in standard form. We have also seen the minimization linear programming problem in standard form. Uh, if we compare them, here is the comparison. The comparison of the linear programming standard forms. First of all, the maximization problems and minimization problem. The objective function is maximization and minimization. That is very obvious because we are talking about maximization problem and minimization problems respectively. Then the constant type. The maximization problem, the standard form is less than equal to, right? And for minimization problem, the standard form is greater than equal to. This must be remembered very much, that the maximization standard form is less than equal to and minimization standard form is greater than equal to. And the variable type is greater than equal to 0 and greater than equal to 0 in both sides. So difference is the objective function is different, constant types are also different. However, the variable types are same. So that is the comparison of the linear programming standard forms. Now, after that, let us now see that what happens if we have a non-standard problem. Now, the non-standard problem can be one of maximization, can also be one of minimization. The constant type could be any of the three, that is less than equal to, greater than equal to, or equal to. Here also there can be less than equal, greater than equal to, less than equal to, or equal to. All right, so this is the standard form, so that is written first. But then other forms of the constants can be now, one thing should be remembered, that although we are saying that constant type could be one of the three, it doesn't mean that all constants should be less than equal to, or all constants should be greater than equal to, or all constants should be equal to. No. One constant may be less than equal to, one may be greater than equal to, one may be equal to, or all may be greater than equal to. So all kinds of situations can actually occur. Similarly, the variable types also can be three types: greater than equal to 0, less than equal to 0, and unconstrained in sign. What is the unconstrained in sign? It actually means that the variable can be any value from minus infinity to plus infinity. Is it all right? So it could be negative, or even if you think that the value should be finite, then minus finite value to plus finite value. All right, so this means that we do not know what is the range of the, and therefore we say that this is unconstrained in sign. All right, so all the combinations can be there in a maximization problem, can also be there in a minimization problem. So far we have seen how to handle maximization problem in standard form, but we have not seen how to handle maximization or minimization problem in non-standard form. So in today's class, we are going to discuss some of these problems where they are not in standard form, but they are in non-standard form. So if the problem is in non-standard form, what should we do? Now, handling different constant type. That's the first thing. So irrespective of the type of objective function, that is maximization or minimization. So we don't have to bother whether it is a maximization or minimization. Only thing we should remember is that what is the constant type. So if the constant type is less than equal to, use a slack variable. If the constant type is equal to, use an artificial variable. And if the constant is greater than equal to, use a surplus variable and an artificial variable. So one should really understand what does all these things mean. See, first of all, this point I have said repeatedly, but no problem repeating it again. That is one of the very important part of the linear programming problem is that the basic variables must be in the canonical form. That means the basic variables in the constraints after the augmented problem is obtained where the inequalities are transformed to equalities, then the basic variables should form an unity matrix. That means 1, 0, 0, 0, 1, 0, and 0, 0, 1 for a 3 by 3 problem matrix. Now, if that is so, then uh, for when you have less than equal to, along with the constraint, if you add a slack variable, automatically the slack variable coefficient is 1. So different equation, different constraint in equation, different slack variables to make it equality in the augmented problem. The slack variables will form a unity matrix and the canonical form will be maintained. So there is no problem there. All right. But if it is equal to, then we do not have any slack variable. So we have only standard variables which are also occurring in all the equations. So we cannot get a canonical form. That means an unity matrix will not be possible to have. So when that happens, how exactly we should take care of this? So when we have a constant type equal to, we have no choice but really to add a variable which is neither a slack variable nor a surplus variable, but this variable is used purely to bring a canonical form. It has no other purpose. It has no physical significance. All right, this variable, because canonical form is not maintained, to bring the canonical form, we have to get an variable which is an artificial variable. Our purpose is to remove them as early as possible because they are artificially constructed only to get the canonical form. Sometimes the artificial variable, particularly in greater than equal to, also represents an infeasible solution. So that also should be remembered. So when we see various problems, we shall see that. Now, when we have greater than equal to type of constraint, here, why do we need a surplus variable as well as an artificial variable? You see what is happening. When you have, you see the LHS is bigger than the RHS. So you have to deduct something from LHS, which is we are calling a surplus variable. So when you deduct that, then the coefficient attached to that variable will be -1. Is it not? Because LHS is greater than equal to RHS. Now, if you want an equality in the augmented problem, then you must deduct something. So LHS minus surplus variable equal to the RHS. So now what happens? The surplus variables are unique in equations, but their coefficient is -1. So we need 1 and we don't need -1. If you multiply the entire LHS with -1, the LHS part is fine. That also will be +1, but the RHS will be a negative value. So we have to then start the simplex first table with a negative value, which is also not allowed in the normal simplex procedure. All right. So we cannot simply multiply a -1, and that also we cannot do in a normal simplex because in that case the value will be negative. So we have no other choice but really also to add an artificial variable there. Fine. So this is how you have to handle different constraint types. Now handling different variable types. Irrespective of the type of objective function, that is maximization or minimization, the variable types are handled in the following manner. If it is greater than equal to 0, usual, that is no intervention is required. So there is no problem at all. But if it is less than equal to 0, then replace the variable x with another variable y, where y equal to minus x, and with then y should be greater than equal to 0. So all that we have to do, replace wherever x is there, replace it by y, and y equal to minus x. So in the substituted problem or the transform problem, we have a situation where all the variables are greater than equal to 0. So no problem at all. But if it is unconstant in sign, that is an unique case because it is unrestricted in sign. So how to handle this? So you see that is also a good solution is available, that is replace the variable x with two other variables. What are these two other variables? Y and right, where y minus z equal to x, where y greater than equal to 0 and z also greater than equal to 0. So if you take two variables y and z which are both greater than equal to 0, but their difference could be positive, could be negative, could be 0. Is it all right? So therefore, depending on the values of y and z. So if you make the substitution, that is y minus z equal to x, then we can actually handle the situation that is unconstant in sign. All right, so we now have understood that if the variable type is greater than equal to 0, no intervention is required. If it is less than equal to 0, substitute y equal to minus x, and if the variables is unconstant in sign, then replace it with y minus z equal to x, where both y and z are greater than equal to 0. All right, so this is how we can handle different variable type. Now let us take some examples to understand how to solve linear programming problem in non-standard form. So here is a linear programming problem. Minimize z equal to 2x1 minus x2 plus 2x3, subject to minus x1 plus x2 plus x3 equal to 4, minus x1 plus x2 minus x3 equal less than equal to 6, and x1 is less than equal to 0, x2 is greater than equal to 0, and x3 is unrestricted in sign. So let us say how many things are in non-standard form. Let us see that first. So first of all, it's a minimization problem, and a minimization standard form is greater than equal to, but it is not in standard form. One constant is equal to type, another constant is less than equal to type. Less than equal to is good because we only have to have a slack variable. We don't need any artificial variable. But in equal to constant, we must add an artificial variable in order to get the augmented problem. Now x2 is greater than equal to 0, no problem there. But x1 is less than equal to 0. So x1 needs replacement. x3 is unrestricted in sign, so x3 also needs replacement. Is it all right? So here is in nutshell, the problem is in non-standard form. It is one of minimization. One constant is equality constant, and we do not even have non-negativity constant satisfied. So without satisfaction of the non-negativity constant, we cannot solve the problem by simplex algorithm. So simplex requires that all the variables must be greater than equal to 0. All right, so we have to do all this substitution. So what kind of substitution? Already we discussed how to bring the problem in a form so that non-negativity constants are satisfied. So y1 equal to minus x1, y2 equal to x2, and y3 minus y4 equal to x3. And y1, y2, y3, y4, they all are greater than equal to 0. So why does this substitution work? Because once again, let us say x1 is less than equal to 0, not allowed. So we make y1 equal to minus x and y1 is greater than equal to 0. x2 greater than equal to 0, no problem. But since everything is y, we also transform x2 equal to y2 and y2 is greater than equal to 0. And x3 is unrestricted in sign, so x3 can be replaced by y3 minus y4. All right, so all the substitutions are done, and after the substitution, the LP problem will take a different form. What is that form? Let us understand this. So it should be minus 2y1. Second part, x2, that remains same, so minus y2. So minus 2y1 minus y2 and plus 2y3 minus 2y4. All right, and here this will be y1 plus y2 plus y3 minus y4 equal to 4. And here y1 plus y2 minus y3 plus y4 less than equal to 6. And all the variables are greater than equal to 0. So after substitution, that is what we are going to get. So exactly that is written here. That is minimize z equal to minus 2y1 because x1 is replaced by minus y1 minus y2 plus 2y3 minus 2y4 because x3 is replaced by y3 minus y4. So this substitution is also written here. All right, so this because in the function, in the objective function, there are three negatives. So you can transform it to a maximization problem. Maximize z equal to 2y1, the negative of this. So minimizing the negative of z, is become maximization. So, maximization will be if some function is minimization, if you take the minus of it, then it will be one of maximization. So maximize z equal to 2y1 plus y2 minus 2y3 plus 2y4. All right, so this is our new objective function. The first constraint, because minus x1 is become y1, x2 has become y2, and x3 has become y3 minus y4. So y1 plus y2 plus y3 minus y4 equal to 4. And the second constraint, y1 plus y2 minus y3 plus y4 is less than equal to 6. And all y1, y2, y3, y4 are greater than equal to 0. So we have already transformed this problem in after substitution, and we see that the constraints are not standard definitely, but the variable types have become all standard. All right. Now how to handle these two constraints? First of all, an equality constraint. So we need an artificial variable, and less than equal to 6. So we simply need a slack variable. So if we do those kind of substitutions, then obviously we are going to get this new thing. Now the big M method is followed whenever we have equal to or greater than equal to constants in the original LP problem. In such situations, artificial variables are required to bring the problem, the equations, in the problem in a canonical form in a augmented problem. The artificial variables has no practical significance. They are there simply to bring the equations out of the non-feasible solution. Because artificial variables are required because the problem is not feasible, to make it feasible, artificially we are taking the artificial variables. The artificial variables should not remain in the final solution. To get out of them quickly, they are associated with negative very high profit minus m in a maximization problem and plus m in a minimization problem. Because look here, they have no practical significance. They are taken only to bring the equations to the canonical form. But in case of greater than equal to, they also mean that artificially an infeasible point has been made feasible. So that will be more clear once we go ahead with the example. Now, this is the substituted LP problem. Maximize z equal to 2y1 plus y2 minus 2y3 plus 2y4 subject to these constraints. Now, artificial variable is added and slack variable, y5 is added. So maximize z equal to 2y1 plus y2 minus 2y3 plus 2y4 plus 0y5 minus ma1. That is the objective function of the augmented problem. And in the first constant, we added a1, that is the artificial variable, equal to 4. And in the second constant, a slack variable y5 equal to 6. All right. Then y1 greater than equal to 0, y2 greater than equal to 0, y3 greater than equal to 0, y4, y5, all and even a1 all are greater than equal to 0. A1 is artificial variable associated with minus m profit coefficient. Is it clear? So that is how we form the augmented problem. Once we have the augmented problem, now we can begin our simplex procedure. So this is our simplex first table. In the very first table, we see that A1 and y5, the values are 4 and 6. Look at the augmented problem, and the coefficients are 1 1 1 minus 1, here 1 1 minus 1 and 1, and this y5 and a1, they form the unity matrix in that order 1 0 0 1, so that the canonical form is maintained. All right. So now if we compute Cj minus Zj values, we find that Zj here is minus m. All right. And Cj minus Zj, 2 minus or minus m, so m plus 2. Here the Zj value for y2 is minus m again. And Cj minus Zj therefore is Cj minus Zj. Cj is 1, Zj is minus m. So 1 minus or minus m, m plus 1. By the same logic, this would be m minus 2 for y3, and for y4 2 minus m. All right, so now this is a maximization problem, so best possible value should be taken. Best possible value is m plus 2, so therefore y1 should come into the basis. Now which one is the bottleneck resource? Here 4 by 1 4, 6 by 1 6. So a1 is the bottleneck, and therefore a1 should leave the basis. All right, so this is very straightforward. Y1 is the entering variable, and the artificial variable A1 is the leaving variable. Since A1 is having very high negative profit coefficient in a maximization problem, it can never come back in the basis. Hence, the variable can be dropped from the next table. So this also is another very important thing, because look here that it has a minus m, which is a very high negative value. So once it goes out of basis, chance of it is coming back into the basis is not there, right? It can never come back into the basis. Since it can never come back into the basis, we can simply drop it, and in the next table, we need not even consider this variable. All right, so this is the advantage we shall take, and we shall drop A1 completely from the table. So here is the second table. In the second table, we have dropped A1, right? Now in the key row, we divide everything by the intersecting element, which is 1 in this case. So no change. A1 is replaced by Y1, and the values are 4, 1, 1, 1, minus 1, and 0. All right, same value. And the key column has to be replaced by 1 and 0, because it has to have a canonical form. So it will be part of the unity matrix, and y1 and y5 together, that is 1 0, and for y5 0 1, together they should form the unity matrix. All right, so that part is fine. Rest of the elements can be obtained by the simplex formula. That formula is old item minus corresponding key row into corresponding key column divided by the intersecting element. So this 2 is obtained by 6 minus 4 into 1 by 1. So 2. And this 1 is changed to 1 minus 1 into 1 by 1. That is 1. So 1 minus 1. So for y2, the coefficient becomes 0. For y3, minus 1 into 1 by 1, so minus 2. And this 1 minus 1 into minus 1 by 1, so 1 plus 1, 2. and this 0 becomes in this case also that is changed accordingly. Now the Cj minus Zj values are also obtained, and the Cj minus Zj value we can find as, because this is 2, so 1 minus 2, so minus 1. And here, you shall have, you can see that that should be 1 minus 2 minus of minus 2. So sorry, minus 2 minus 2. So minus 4. And this one 2 minus of minus 2. So plus 4. All right, so this is a maximization problem. So y4 is going to then come into the basis because that has got the maximum Cj minus Zj. And between them, which variable is going to be bottleneck? Let us see in the next table. So this is our simplex third table. That is the second table. In the second table, this is the third table. So in the second table, once again, let us say that when if y4 comes into the basis, which variable should leave? Because you see this is minus 1. So these 4 divided by minus 1, it has no meaning because it doesn't require any resource. It is actually releasing resource, so that y1 will never be the bottleneck resource. That means the y5 is the only thing left that should be the bottleneck resource, and 2 by 2 equal to 1. So we have that y5 should be leaving and y4 should be entering variable. All right, so y4 now enters, and as y4 enters, first of all, we write the key row by dividing everything by the intersecting element. So it should be 1 0 0 minus 1 1 and half. And the remaining coefficients are also calculated. First of all, the key column becomes 0 1 because y4 and y1 and y4 should form the unity matrix. This 4 would be 4 minus 2 into minus 1 by 2. So it should be 5. Similarly, all the other coefficients are calculated, and Cj, the Ci values are changed. So, then y1 is, and so y2, this is a candidate. It is not in the basis. So it should be 1 minus 2 into 1. So minus 1. What about y3? Minus 2, 0, and minus of minus 2. So 0. And y5, 0 minus 2 into half minus 2 into half. So minus 2. All right. So you see the Cj minus Zj values are all negative or 0, but not positive. That means optimal solution is obtained. All right. So then we say that third table is optimal in itself. And however, there is a issue here. The issue is there is a 0. See, this 0 means that y3 can come into the basis, right? Y3 can come into the basis, which might give us an alternate solution, but that alternate solution is not going to be meaningful. That is because, nothing can come into the basis because look, 5 by 0 and 1 by minus 1, there is no bottleneck resource. So we may get into a problem if we try the alternate solution. There is a reason for this happening. Why it is happening, I'll explain. But before that, let us look at the simplex optimal table carefully. And, the solution is obtained. And note the 0 value in the Cj minus Zj of the non-basic variable y3. What significance does it have? So that significance I will explain. But one more thing also, you see that the solution obtained is not for the original problem. The solution is for the substituted problem, right? That solution is y1 equal to 5, y2 equal to 0 because they are non-basic, y3 equal to 0, and y4 equal to 1. So what should be the value of z? The value of z should be 12 because these are the profit coefficients 2, 1, minus 2, and 2. So 5 into 2, 10, 0 into 1, 0, minus 2 into 0, 0, and 1 into 2, 2. So basically these 2 and these 2 are significant for y1 and y4. So for y1, 5 into 2, for y4, 1 into 2. So total is 12. So that is the optimal solution, but that is not the optimal solution for the original problem. This is the optimal solution for the substituted problem. That must be remembered. Right. So if we remember the substitutions is that if y1 equal to 5, then x1 should be minus 5, because transformation is y1 is minus x1, that is x1 equal to minus y1. Now y2 and x2 are equal, so if y2 equal to 0, then x2 should be 0. And what should be x3? x3 is y3 minus y4. So y3 is 0 and y4 is 1. So x3 should be minus 1. Is it all right? So these are the x1, x2, x3 values. And since the objective function is 2x1 minus x2 plus 2x3, so that should be minus 5 into 2, that is minus 10, and minus 1 into 2, so minus 2. So therefore, minus 12. So minus 12. So this is our going to be the optimal solution of the original problem. All right. Now, before we move further, let us see about that 0 value and why that is going to create a problem. Look here, particularly for y3 minus y4, actually, it is in the original problem, the substitution is that, y3 minus y4 is, if you go back one more slide, then you see y3 minus y4 is nothing but the x3. So it is actually, although we are doing in the y domain, but really speaking, this y3 minus y4 is important to us. We are not interested in individual values of y3 and y4. Is it not? Because the original problem, it is the y3 minus y4 that is important. So if the y3 value is, y3 minus y4 at their minimum possible values, that is one thing. But in fact, if you look at the final solution, the optimal solution says y3 equal to 0 and y4 equal to 1. So if that is so, so it is that minus 1, which is the value that we are interested, that is 0 and 1. But for the time being, just assume that if y3 is 20 and y4 is 21, is it not? So even then y3 minus y4 will be minus 1. So you see what is really happening. It is not the individual value that is important. It is the relative value that is important. Basically, it is the y3 minus y4, and even the coefficients are also such so that, they individually they cancel each other, because even here it is minus 2 y3 minus y4. That is how you can interpret. So what is happening? Basically, the bound of y3 and y4 is not there. Since the bound of y3 and y4 is not there, it is only the relative value between y3 and y4. Therefore, if you try that alternate solution, you may come up with a value that is y3 equal to infinity and y4 is also infinity. Or maybe you can say infinity plus 1, whatever it means. So you see, that is the problem that are associated with such kind of substitutions. But we don't have to worry, because we don't have to really bother about the alternate solution as long as we have got our optimal solution, that is the best possible value, that is good enough for us, right? So this is the significance of this alternate optimal solution. So we have also seen that how the simplex optimal table is obtained by suitably transforming and getting back to the original problem. Right, so here is another second problem. In this problem also, we have minimize z equal to 3x1 minus 3x2 plus 6x3 subject to 2x1 plus x2 plus 2x3 less than equal to 44, x1 plus 8x2 minus 6x3 greater than equal to 52, 5x1 plus 3x2 equal to 20, and the absolute value of 4x2 plus 7x3 less than equal to 90, and x1 greater than equal to 0, x2 also greater than equal to 0, and x3 is unrestricted in sign. So write the augmented problem and draw the simplex fast table. Is it all right? So this is what is asked for this problem, because once you can write simplex fast table, definitely we can solve without any problem. So let us analyze this problem before proceeding further. It is a minimization problem. And first of all, the constants are one is less than equal to non-standard form. This one is greater than equal to standard form. This is equal to non-standard form. This is less than equal to non-standard form. Whereas x1 and x2 are in standard form for minimization, they are because both are greater than equal to 0, but x3 is unrestricted in sign. Is it all right? So what kind of various things that we require? First of all, for these constant, we need a slack variable because it is less than equal to. This is greater than equal to, so we need a surplus variable and an artificial variable. This is equal to, so we need an artificial variable. But this one is problematic because this is an absolute value what we have to take of 4x2 plus 7x3. So how to handle this constraint? This is interesting. Let us see how exactly we go ahead. So the problem is non-standard form. The problem is one of minimization. One constant is an equality. Another two are less than equal to. But only absolute value is to be taken in the LHS of one constant. X3 is unrestricted in sign. Non-negativity constants are not satisfied because one of them is unrestricted in sign. So these are the various issues of non-standardness of this particular problem. Once again, there is an variable type which is unrestricted in sign. There are constants which are less than equal to, greater than equal to, and less than equal to. So all kinds of constants. Additionally, there is a constant with an absolute value to be taken. So first, if we do things about the variable types, so we know that x3 should be replaced by y3 minus y4, is it not? And x1, x2, no issue. So to transform in y domain, we can say y1, y2, and y3 minus y4 for x3. All right. So if we do this substitution where y1, y2, y3, y4 are all greater than equal to 0 and bring the problem to the y domain. And also if we rewrite the problem as one of maximization because two constants are less than equal to type. Although that is not required, but we can just do it. That's all. So this is how the substituted problem would look like. Because x1 and equal to, these are the substitutions, that is x1 equal to y1. So when we do minimize to maximize, we take a minus of this. So 3x1, so it will come minus 3x1 plus 3x2 minus 6x3 maximize. So since minus 3x1 and x1 equal to y1, so in y domain it will be minus 3y1. Now this is plus 3x2 for maximize. So this should be plus 3y2. Then plus 6x3 has become minus 6x3 for maximization. So it should be minus 6y3 minus 6y3 minus y4, or minus 6y3 plus 6y4. All right, so that is our substituted problem objective function. And the constants can be rewritten. So 2y1 plus y2 plus 2y3 minus 2y4 should be less than equal to 44. y1 plus 8y2 minus 6y3 plus 6y4 should be greater than equal to 52, because minus 6x3, x3 is y3 minus y4, so minus 6y3 plus 6y4. And this one is simple substitution, 5y1 plus 3y2 equal to 20. And this one, 4x2 plus 7x3 will become 4y2 plus 7y3 minus 7y4 absolute value greater than equal to 90. So one problem still remains, how to handle that absolute value type of constraint. So how to handle, this is a substituted problem. Now, how to handle the constraint with absolute value of the LHS? Very simple answer. It can be replaced by two constraints. One is that plus orbit, another is minus orbit. Both should be less than equal to 90. So the plus of that means instead of one constant, we have to add two constants. One will be 4y2 plus 7y3 minus 7y4 less than equal to 90. And the other one will be minus of the whole thing less than equal to 90, which comes to minus 4y2 minus 7y3 plus 7y4 less than equal to 90. All right. So this is how this can be handled. So originally we had four constants. Now we have five different constants. All right. So this is how then the substituted problem would look like. Maximize minus 3y1 plus 3y2 minus 6y3 plus 6y4. The first constraint less than equal to 44. Second constraint greater than equal to 52. Third constraint equal to 20. Fourth constraint less than equal to 90, and fifth constraint less than equal to 90, and all y variables are greater than equal to 0. And now we have to do something when we get the augmented problem. This one needs a slack variable. This one needs a surplus variable and an artificial variable. This one means less than equal to, and then greater than equal to needs a surplus variable and an artificial variable. The third constant needs an equal to, so an artificial variable only. Fourth and fifth constants both are less than equal to, so each of these constants only need slack variables. Is it all right? So that is how the substituted problem can be converted to the augmented problem. So here is our constant, here is our augmented problem, and since it is one of maximization, so we had to had a minus m attached to the two artificial variable, and 0s3 plus 0s4 and 0s1 0s2. So this is will look like in the first constraint plus s1 because it's a slack, second one minus s2 plus a1 because it's a greater than equal to type, so we have a surplus variable and an artificial variable. Third one is equal to type, so an artificial variable, and third and fourth and fifth has s3 and s4, two slack variables, and therefore all the five constants are taken care of. Now all these variables y1, y2, y3, y4, s1, s2, s3, s4, a1 and a2 all should be greater than equal to 0. So this is how we have been able to put the augmented problem. So once we have put it in augmented problem, we can write the simplex fast table from here. The basis S1, A1, A2, S4, values 44, 52, 20, 90, 90. The Cj values are written from the objective function. Ci values are also written from the objective function. And if you analyze it, then Y2 has the maximum value, that is 11m plus 3. Obviously 3 is too small, so ignored. So y2 will come into the basis, and a1 is the bottleneck resource, so a1 should leave the basis. All right, so this is, and then we can proceed with the simplex and try to solve the problem in its entirety. Is it all right? So this is how you can solve this kind of problems, and you can tackle what you say that non-standard problems. So we have discussed different types of non-standard problems. We see that there are variable types. So if the variable type is greater than equal to 0, there is no issue. No substitution is required. If it is less than equal to 0, then a minus y1 instead minus y value has to be taken. And if it is unrestricted in sign, then it should be the difference of two new variables. All right. So all these things, we have seen in this particular problem. Now, quickly we go through a third problem, and so that our understanding becomes much better. So this problem is maximize z equal to x1 plus 2x2 minus x3 subject to 2x1 plus x2 minus 3x3 less than equal to 5, minus 4x1 minus x2 plus x3 less than equal to 4, and x1 plus 3x2 less than equal to 6. And all x1, x2, x3 are unrestricted in sign. Alright, so how to handle this particular problem? One thing is clear that constraints have no problem. You simply add a slack variable in each of these. But x1, x2, x3, they are unrestricted in sign. So they should be replaced by difference of two variables, each one of them. That means instead of three variables, we now are going to have six different variables. So this is exactly what we do. The substitution x1 equal to y1 minus y2, x2 equal to y3 minus y4, and x3 equal to y5 minus y6. When you do that, this particular problem will get transformed, and this is going to be our transform problem. That is, maximize z equal to y1 minus y2 plus 2y3 minus 2y4 minus y5 plus y6, and subject to after transforming this, and all these variables are greater than equal to 0. So that will be our substituted problem. Thereafter, the substituted problem, if you add the slack variables, that is S1, S2, S3, then we get what is known as the augmented problem. So we have the original problem, that is the substituted problem, and then we have the augmented problem. By adding slack variables, we have the augmented problem. Now, in order to solve this, let us see, this is the simplex first table, right? S1, S2, S3, they are in the basis, and all the CIs are 0. The values are 5, 4, and 6. The coefficient matrix are all written between y1 to y6. And the S1, S2, S3, they form an unity matrix so that the equations are in canonical form. The objective functions are also written, and since zj equal to 0, the cj minus zj values are also easy to compute. So this is one of maximization problem. So we have to take the best possible value, most positive value. So obviously it is clear that y3 should come into the basis, is it not? Because 2 is the highest. So which one is the bottleneck resource? 5 by 1, 4 by minus 1, and 6 by 3. So it is the 6 by 3 which gives the bottleneck resource. So that means S3 should be leaving the basis. So exactly that is what S3 leaves the basis and Y3 enters the basis. Alright, so that is the simplex first table computation. Now from the first table, now Y3 has come into the basis. All the coefficient values are recomputed, and all the Cj minus Zj values are also recomputed. So at this point of time, if you see that Y6 has the maximum value, that is 1. So Y6 should come into the basis, and this is not a bottleneck resource because it is releasing resource. This doesn't need any resource, so cannot be bottleneck. So S1 should leave the basis because 3 by 3, that should be the consideration. So obviously then Y6 now enters the basis and S1 should leave the basis. All right. So new value here, Y6 should come here, and this value should be 3 by 3 equal to 1. All right. So that value has been computed once again. So 172, and all the coefficients are computed. The Y6, S2, and Y3, that is Y6, S2, Y6, S2, and Y3. I think this is wrong. That value should be 1. They should form the canonical Y6, S2, and Y3. They should form the canonical matrix, canonical form. Now again, if you compute, now you see that Y2 is the entering variable, right? So Y2 is entering variable, and S2 should be the leaving variable. So once again, when you compute, this time we find that y6, y2 and y3 that come into the basis. And when that comes into the basis, the values are 9 by 4, 9 by 4 and 11 by 4. All right, so these values are obtained. So as the Cj minus Zj values, they become all negative. So therefore, optimum solution is reached. However, zeros in the Cj minus Zj value for some of the non-basic variable indicate the presence of alternate solutions. You see, these we have already explained that these zeros are coming because these alternate solutions are going to be because of the difference is important. So that is the difficulty we might get if you try to get the alternate solutions. But then once you get the solution that y1 0, y2 is 9 by 4, y3 is 11 by 4, y4 0, y5 0 and y6 9 by 4. You see, we did not get all these values. We got only y2, y3 and y6. Other variables are non-basic. So y2, y3, y6 as values and they are non-basic, so they are at 0 level. All right, so these values and z can be computed. The z is 22 by 4 based on this objective function. So we got the optimum solution, but nevertheless, there is a problem. The problem is that this is not the solution that we want. We want the solution of the original problem. So x1 should be y1 minus y2, x2 should be y3 minus y4, and x3 should be y5 minus y6. So that transformation has to be worked out. All right, so when we look at that transformation, we compute x1 minus 9 by 4, x2 11 by 4, and x3 minus 9 by 4. So what should be z value? The z value will be x1 plus 2x2 minus x3, and that would come to 11 by 2. So 11 by 2 will be our new z value, and that z value we can then put, and then we see that that is our optimal solution, right? So we stop here, and thank you very much for listening patiently.